In the last lesson, we saw that you could predict the shapes of the orbitals by looking at the orbital angular momentum quantum number. That was script L. So when L was 0, you had no nodes through the nucleus. You can think of a node as a cut through the electron cloud. There are no cuts with L equals 0. So if you look at the kind of cloud that you get, it looks like this. Your cloud can reach right into the nucleus, and it looks kind of spherical, the shape of the orbital. This is called an S orbital, or the subshell it's in would be an S subshell. Any S subshell will only have a single S orbital in there. Now, if L equals 1, you have one cut through the cloud, through the nucleus. It passes through the nucleus. So it's a nuclear node, we call it. And that's going to cut the cloud into two pieces. You're going to have a lobe on either side of the node. The nucleus is right there. This is a p orbital. In a p subshell, there are 3 p orbitals, and they each are oriented different ways. One goes along the x-axis, another the y-axis, and one on the z-axis. Now when you've got L equals 2, you have 2 nodes that cut through the nucleus being right in the center there. And that's going to cut your cloud into 4 lobes. So you get this kind of cloverleaf shape. This is a d orbital, we said. And in a d subshell, you've got 5 orbitals. Finally, if L equals 3, then we've got 3 nuclear nodes that cut through the nucleus. Here's the nucleus in the center here. They're going to cut the cloud into 6 lobes. And some of the F's look like this. There are different ways that you can cut things, and we talked a little bit about that in the last lesson as well. But this is an F orbital, and in every F subshell we said there are 7 F orbitals. Now remember that N controls the size and the energy of an orbital. The bigger N is, the bigger the energy is. That's because you've got a larger orbital when you have a bigger N. So when you have N equals 1, you have a fairly small orbital, and the electron can get close to the nucleus. Now, anytime that you've got the electron close to the nucleus, the energy is lower. If you pull the electron far away from the nucleus, you're putting some work in, so that's going to make the energy go up. So a bigger orbital will have higher energy. And you can see that trend here. If you go from a 1s to a 2s to a 3s to a 4s, they're bigger and bigger orbitals. So you're going to have higher and higher energies. So you can look at the N value and decide right away which orbital has a higher energy, you would think. And then you can go and look at the L value. Now that tells you how many nodes go through the nucleus. Now, we just went through how L relates to those things, but if you've got a higher L value, you have more nuclear nodes, so the electron can't get close to the nucleus, so you have a higher energy. Okay, so it seems pretty basic. We can decide what order the energies for a set of subshells should go in by looking at N and L. The bigger N, the higher the energy. The bigger L, the higher the energy. But sometimes those two things fight each other. Let's take a look at what the orderings actually are. If you look at 1s, you would expect that to be the lowest energy subshell, and it is. It's the lowest energy because it's got N equals 1 and L equals 0, which are the lowest possible values for those two quantum numbers at once. So that'll be the lowest energy subshell out of all subshells. The next one up is 2s, which makes sense. You increased N, so you should have a higher energy than 1s. The next one up is 2p. That also makes sense. The 2s and the 2p are roughly the same size, so and the n is, the n is the same for both of them. The only thing that's different is that in the p you have a nuclear node, so it's going to elevate its energy a little bit. So I would explain 2p is higher than 2s because it has a higher L value. Okay, and then if I go and look at the 3s and the 3p, that all makes sense too. Wait, where's the 3d? If I look at where the 3d comes in, it comes in above the 4s. Now, those two effects are fighting each other here. The 4s should have higher energy because it has a bigger n value. It's a larger orbital. The 3d should have a higher energy because it has nuclear nodes. It's got 2 nuclear nodes, and the 4s doesn't have any. So that should make its energy higher. So obviously that second thing wins. So sometimes when you have a tug of war, it's not immediately obvious which one's going to win. The 4s comes in lower energy than the 3d. And then the 4p, which you expected to come after the 4s, comes in. And you can see as you go up that this thing with the d's fighting the n's, the l's. So you have the L quantum number fighting the N quantum number for ordering these two. The L quantum number is winning here because the 4D has a higher energy than the 5S. And this pattern seems to hold up. When you get to the 6S, then the 4F comes in. So the 4F, which has a lot of nuclear nodes, which make its energy very high, it's not going to be down here with the other 4s, comes in after the 6S, and then the 5D comes in. So you can see that this ordering isn't as easy as we hoped it would be. Just knowing a bigger N gives you a bigger energy and a bigger L gives you a bigger energy doesn't help you get the exact ordering here. But there is something that you can look at that will help you get the exact energy level ordering for the subshells. Now, our job here is to get the energy ordering of the subshells correctly. We want to take the subshells and list them in order of lowest energy first up to highest energy. All right, now the periodic table can help us. This is really kind of a stylized periodic table that I have here on this frame. Now, if I look at the row on the periodic table, that corresponds to the N quantum number, the principal quantum number. And if I look at the region that I'm in on the periodic table, that actually corresponds to the L value. How? How does this work? Well, if I look at the first 2 columns in the periodic table, those are filling up S subshells. So we call this the S block, the first 2 columns in the periodic table. Now, if I look over here at the 6 columns that are over here, this is the P block. I'm filling up P's. So when I'm in the second row and in the P block, I'm filling up a 2P. When I'm in the third row in the S block, I'm filling up a 3S. Third row in the P block, I'm filling up a 3P. Okay, so far so good. That works fine with the S's and the P's. When I get the 4S, remember we just said that the 3D is above this. It won't start filling until after the 4S is filled. So you have to put your electrons in the 4S and then the 3D starts. So you can see the shape of the periodic table is reflecting the subshell energy level ordering. So 4S, it goes 4S to 3D to 4P, then you go down to the next row. 5S to 4D to 5P, then down to the next row. 6S, okay. Now, right here, there's a bypass on the periodic table. These 2 rows down here should be really squeezed in right here. So after the 6s, it goes down to the 4f. And then it comes back up and it does 5d and 6p. Now, when you go down to the 7s next, that goes down to the 5f. And then that comes up to the 6d and the 7p. So you can take a look at this and get the subshell energy ordering from the periodic table. And I'm asking you to do that with some subshells in the question below.